So thanks everyone for joining today. My name's Jeff Dion. I'm one of the co-creators of the JCore open source project. We have Rob Landley here also.
Hello.
And hopefully today we can tell you a little bit about what it is we've done here and why that's cool. So I think the first thing is, what is this? Maybe many people don't know exactly what JCore is. As someone had mentioned, it's an open implementation of specifically the Super H compact instruction set architecture. That's a CPU core architecture from the late 90s.
It was the best-selling hardware. It was the best-selling CPU in the world for 3 years. It was a very big deal that was sidelined for reasons that had nothing to do with the technology. It was global financial things, IP passing from company to company.
And the good thing about it is it's patent clean. So instead of making something brand new and hoping that there are no submarine patents, we know for a fact, because it's been in the marketplace for now over 20 years, that this is an intellectual property clean implementation. The instruction set architecture has no problems, and it can be used. The fundamental patents on the way the instruction set architecture is encoded eventually led to something called ARM Thumb, which everybody is probably familiar with. Obviously, those patents were not expired when ARM was using them, so there's some financial implications for ARM from that they ended up having to deal with. The JCore family implements SH Compact Plus. There are extensions for symmetric multiprocessing and to make efficient use in FPGAs and ASICs. But generally speaking, it's a contemporary CPU core to Motorola 68000, but a real step up from something like that.
So not exactly contemporary, slight successor, but we'll get into timelines later.
Yeah. So why did we build something like this? Why did we spend the time to make a CPU core architecture? Well, it was purpose built for connected embedded systems. We build energy monitors, devices that work in critical infrastructure on the electricity grids. And the JCore architecture is deployed in such critical infrastructure applications and has been now for 5 or 7 years. It's a well-tested set of intellectual property. We surveyed the choices that were available at the time: Spark and MIPS, of course ARM, which was patented still, even the older ARM7 devices, and OpenRISC. We found that Super H had done a lot of work on the design of the instruction set architecture, not just thinking through what the instructions should do, but studying things like the output from the compiler statistics to make sure that the design was going to achieve the kinds of performance metrics that one needs for embedded systems specifically. That was before things were called Internet of Things. And for us, the main issue was memory bandwidth. We have a lot of DMA going on in our commercial designs, multiple streams of DMA happening simultaneously, sample streams, and we needed to leave as much memory bandwidth available as possible for that kind of thing to happen. The cleanness of the SH architecture, the way that it's designed to work with higher level languages, is really important to us.
If I could point out something. Instruction set density is an extremely important metric. You can express more code in fewer bytes using the Super H architecture than you could anything else at the time, and since then it's gotten more complicated because there's more architectures. There's a lot of positive knock-on effects of that, such as more code stays in cache, you flush the cache less often, that newer architectures have had more resources to play with. So they've gotten less lean. You know, there were entire cul-de-sacs of, you know, Pentium 4 and stuff with long pipelining that when we say it was a local peak in language design space, what is available in FPGA now is analogous to what was available in ASIC some number of years ago. And that local peak has kind of swung around and lined up. So there's a longer conversation to have here, but we did a lot of research on what we should implement. And in fact, Super H was not the first one that we tried for the Synchrophaser project Jeff mentioned. We tried Leon Spark first, and we went, okay, this is there, this is complete, this has the might of the European Space Agency behind it, and it doesn't meet our needs. Super H, of all the architectures we could have cloned, was the best fit for our needs.
And it's really not a surprise that that kind of thing happened with Hitachi doing a massive investment program in Super H in the early 90s. At the time, they were licensing 68K. It was clearly not a long-term solution. 68K had other ideas. This is before Coldfire. But as Rob mentions, you can now do interesting things like emulating Sega games, or even an entire engine controller if you're still interested in internal combustion engines, yet another topic, and replicate the kinds of things that were early design wins for Super H that made it the market leader for a few years in the 90s. And of course, this is just good technology as a result. It's an excellent solid foundation that you can use to build any kind of embedded system on top of an FPGA today. Well researched, we can point you at the patents, and we can point you at the research documents that were published at the time, as well as some of the stuff that we've done. And as I mentioned, J-Core is a clean re-implementation in a dialect of VHDL. The ESA and Jiri Kaesler invented something called the two-process method, which is a very safe way of designing hardware that may appeal more to software engineers than the typical approach that's usually done with IP cores. And J-Core makes extensive use of generators, which we'll talk about a little bit later, so that you can get started very quickly adding things to the instruction set if you want to, or to the SoC buses. Designed from the ground up to do signal processing, networking, and of course to run Linux. The J-Core family is becoming quite extensive now. The ones that are out for public consumption are the J1. It's a simple 32-bit machine. It comes to about 30K ASIC gates. It's a 5-stage pipeline. It still has some DSP instructions. J2, of course, is the one that is the full-up Linux-capable, SMP-capable 50K ASIC gates device. It fits in mostly Xilinx FPGAs, as we'll see a bit later. Rob?
What do you want me to say about this?
So moving up and down from J2, there's also a J0 coming, which is a 16-bit data path double clocked. It'll be about 15K ASIC gates. It'll fit in pretty much a very, very small FPGA, something like a 5K gate. ICE40 will still have half of its space available to use for other.
J1 does fit in an ICE40, but it currently uses most of it. J2 will fit in an LX9, and you'll have like 40% of it left.
That's a Xilinx chip. And J32, of course, adds virtual memory, and a multi-issue version of that is in the works.
I'd like to point out that J2 is the one we released first, and we then went down market to J1. We have J32 code complete, but haven't finished porting Linux to it yet. We've prototyped a J64 to prove to ourselves that yes, this can scale up as high as we need it to, but we found that the current market opportunities are actually at the lower end because the volume of no MMU chips becomes absolutely insane. No MMU chips are to MMU chips a bit like bacterial cells are to mammal cells. There's a whole lot more of them in the ecosystem. They're just invisible.
So in keeping with the topic today of FPGAs and open source FPGAs, this board in the background is one of those energy monitors that we had mentioned previously. And the main chips on that are all FPGAs. There is an ASIC, it's a mixed signal ASIC that we did for that project, but the entire brains of the device is inside an FPGA. At the time that we did that, 2015-16, it wasn't possible to do it with a completely open source toolchain, but later on, another presenter today will talk about how that's changing. J1 at the time, right now, is capable of being synthesized for small FPGAs using completely open tools. The point of this is, if you need to build some system with an FPGA that is more than just a system on chip, J-Core is a good choice for that. It was designed for that in the first place. The IP cores that fit around the CPU do all kinds of very cool things, especially the ones that were used for things like energy monitors.
Yeah, we've done a lot of hard real-time data acquisition where you're not allowed to drop any of the samples and you must respond to them in microseconds or in some cases nanoseconds.
The perfect use case for FPGAs is to do that kind of thing. Now FPGAs are on cost par with microcontrollers, and that's a really interesting statement to be able to make. So you can take J1 directly off of GitHub and put it in an ICE40 Ultra Plus device, which is on the order of $5 quantity one retail. And you end up with a 32-bit CPU that has a full open source tool chain, a well-supported mature tool chain, and 128K of RAM. And that connects to a flash on the outside, an SPI flash for 90 cents, and suddenly you have something that is significantly more powerful than an Arduino, much more powerful than anything else that you could get for the same price. And at the same time, you have 10%, 20% of the FPGA fabric still available to do any kind of device you want to see on the outside of the basic SoC platform.
And you have 128 megabytes or more of SPI flash memory. We have actually run a little system with an ICE40 and an SPI flash and 3 watch batteries. And the only reason there was 3 is that we needed 3 volts. We can probably get it down to 1 later. But the chips are literally smaller than the watch battery. We were thinking of doing a thing where we taped the chips to the front of the watch battery with clear plastic tape and had a little LED that it would blink just so you could see, and maybe an infrared sensor, and just go, this is the tiniest little system running our stuff as a demo.
And it's a really exciting time to be getting into this because all of that can be done with completely open tools now. A $15 FPGA can host a dual-core J2 plus the GPS baseband, and we'll see that later. That kind of thing is interesting for stuff like drones. Unfortunately, the open tools are not quite there yet for all of that. You still need some vendor tools for the FPGAs, but that will probably change. Yeah. Some applications need an FPGA anyway, and when that's the case, the entire SoC comes for free. The good thing about J-Core, and to some extent RISC-V is in the same camp, the same RTL that you use for FPGAs is ASIC ready. You can take a J2 CPU It's 0.45 millimeters squared in 180 nanometer process, and it'll run 125 megahertz without breaking a sweat. It's very easy to see a path from a very small prototype that costs you a few tens of dollars in FPGA to seed the market, and then an ASIC that ends up being pennies per die.
Yeah, Google is doing that Skylake stuff. About how fast would it run at 130 nanometer?
130 nanometer is probably going to be 175 megahertz, maybe 200 if you really push it, but 175.
Okay. Cool.
Of course, the CPU is no use by itself. This is a platform approach. All of the things that we have done are not about proving a CPU. It's about building a system. JCore SOCs can be automatically generated. There's a project in our GitHub that will let you add things to an SOC very easily, to add things to the system on chip. There's a full set of standard peripherals, from memory controllers to cache controllers to Ethernet and LCD drivers. And of course, it's supported by OS toolchain. This is completely open, and our driving philosophy is to democratize the space. There's no need anymore for a large company to be involved when you're talking about your compute platform. You can do it for yourself. There's multiple choices. JCore is one of them. FPGAs make it possible, as Rob mentioned. We're now at the point where commodity FPGAs meet the same end specification as something that you would have to tape out a modern process for in the mid-90s. Hardware platforms to run it are all available on open licenses. You can see a little bit more about that. And there's, of course, mature tool chains and operating systems for all of this stuff.
Yeah, an interesting thing to me is that Lattice, which has the fully open source toolchain, is now making larger FPGAs, although they're much slower than the Xilinx stuff in terms of how fast you can clock them. But even a 33 megahertz processor, that's how fast Linus Torvalds' machine was when he first wrote Linux. Depending on what your application is, if you wanted to do Linux in a fully open source toolchain thing, we don't necessarily need the other vendors are still being proprietary with their toolchain problem solved, because multiple fronts are advancing in parallel and opening up. It's an exciting time.
The entire ecosystem is here as well, and you get all the way from a hardware board with open reference designs and boards you can clone and modify, all the way through to user space applications and utilities. So I think we'll stop and see if there's any questions for our sort of Japanese-derived core, and then we'll move on to what you can do with it.
Yeah, we have some questions and comments. Let me just fish them out.
Yeah.
So someone asked, what's the actual website URL? Is it still j-core.org?
J-core.org is good, and there's a link on there to the GitHub, but we'll also put that up at the end.
Okay.
Yeah, I need to update the content on j-core.org. It's what's there is accurate, but not entirely up to date. There's some newer stuff on our GitHub and on the mailing list.
And just feedback that somebody, Jeremy, had his PhD on exactly the topic of like code density and optimization. So he found it very interesting so far. We've had reports of like people having issues with not being able to see the slides. If you're on the web view, it seems to be that Firefox is working better than Chrome, and generally refreshing your browser has resolved the issue. And that's all for now. So if you want to move on, let's go.
Very good. So what can you do with this? So we freely admit that, and it's sort of a plus on one side, that the JCore ecosystem has been somewhat closed from the beginning because it was designed for specific applications in mind. And this is a board that we did for a big S company in Germany. It uses a JCore SoC in an FPGA. This is a 3-phase energy monitor. It's not a simple thing like a watt meter. This does capture of waveforms in the megahertz region. It does all kinds of digital signal processing. It has secure time and location with a GPS receiver. And this is just one of the boards in that system, but it's sort of an example to get you thinking about the complexity of systems that you might build. And so the landscape for devices goes from Arduino class things with a J1 core in, say, an ICE40 to small devices like a Raspberry Pi class device. We'll show you a board for that later with a dual core J2 running Linux, to large compute intensive or signal processing things, which for me personally is very interesting, and the reason that we did this. And of course, none of these things is possible without good tools, without the FPGA marketplace being ready to build these kinds of devices. So finally, we're getting to the point where these things are practical for the average person to jump into and start working on their kitchen table if they want to do that. And it's very easy to prototype a design with any of the boards that are available. And if your commercial side works out, you can scale to ASIC. Anything 180 nanometer or newer is very practical for this type of migration path from open source FPGA all the way to commodity class popcorn.
An interesting discussion we've had is that there's also a sweet spot in ASIC manufacturing for power consumption, because as you go down from 180 nanometers, the chips get more expensive and they get faster, but they also get more power efficient to a point, and then the newer things like that 5 nanometer stuff they're working on aren't necessarily as power efficient. If you want something where this is going to run off of a watch battery for 6 months, you don't necessarily want an old ASIC and you don't necessarily want a new ASIC. And then we're speccing, well, how long will, for example, an ICE40 FPGA run off of this battery versus how long will the ASIC run off of it? The trade-off isn't necessarily performance, it's power consumption and battery life. So there's a whole bunch of stuff to come up to speed on here, and it's really interesting.
Yeah, and that brings us to the application spaces as well. With just using an FPGA, you can do sort of 4 classes of device with this type of a design flow. You can make small systems. I've prattled on about that for quite a long time. Low power, as Rob mentions, is a big thing. It turns out that those open tools FPGAs from Lattice, the ICE40 series, can get down to something like 100 microamps of standby current. And what that means is 6 months of battery life from a $5 FPGA. 3 milliamps of burst current, power supply current when it's running. So you set the thing up to do maybe Bluetooth low energy, or you set it up to sample some value or temperature or something every once in a while. And then the CPU core goes back to sleep and the FPGA reverts to drawing its leakage current of about 77 microamps. And there's a few microamps left over for the SPI flash. Little machines can be built with reasonable size FPGAs for sub $60. It's interesting to note that when you design like a gateway or a router or any kind of connected IoT device, there's sort of a base cost for the compute engine that is required to run Linux and connect to the network. And that's traditionally been about a $35 device. I'm not talking about the tiny Bluetooth connected things. I'm talking about sort of an Ethernet connected device with a 100 megahertz or above class dual core CPU. And FPGAs
and memory.
And enough memory. And FPGAs are not quite cost parity with that yet, but it's coming really close. You can get about sub $60 for low quantity. including all peripherals. And
how much does the LPDDR2 chip that we're using for the 128 megs for Linux ballpark cost?
it's about $3.50 in 1,000-piece quantities. So
Okay.
it's sort of a reasonable price adder for a system to get the capability to run Linux. And
128 megs is about the low end for running a current Linux kernel comfortably.
Right. And then there's compute intensive and signal processing applications where you might have dedicated coprocessors, or you might have application specific accelerators. And those things fit in larger FPGAs. And speaking with the guys at Google who are looking at all the different tool flows, there is very soon, and I'm sure we'll hear about it in the OSIS in the next PNR talk later, coming very soon will be ultra scale support. And with that kind of FPGA, if your application can afford the cost of an ultra scale FPGA, you can run multiple Linux capable J-core systems in one FPGA and still have enough gates to do massive parallel FFTs or whatever kind of digital signal processing you want.
Just a quick tangent. J2 is an SMP system, and the SH2 chip that we cloned is, well, re-implemented. It's none of our actual circuitry is remotely the same, but the SH2 wasn't SMP, because SMP really started taking over the world between 2000 and 2005, several years later. We actually had to add comp exchange. We had to analyze what Linux needed, and the comp exchange instruction wasn't just for SMP, but futexes assume that it is available, which the older architecture didn't have, and you had to awkwardly work around with test and set loops, and it was very inefficient. This isn't just, oh, there was a perfect old technology. This is, we had to reevaluate what do we actually need in the modern world. This was a very good base, but we spent 5 years dogfooding it and basically going, okay, we're putting it in these things, we're running current systems on it. What are the issues we're seeing? What are the bottlenecks that are happening? What are the things that we could improve based on actual real world use on a daily basis? And that's a very important part of the development process. You don't use the waterfall method where you say, here is the design we're going to start with, and we resolve not to learn anything at any point in the process until we're done. There is a constant feedback loop. That's always been one of the strengths of open source development, and one of the reasons we wanted to get it out there for other people to bang on as well. But we've been doing that internally from day one as how we made this SoC.
And the reason we were able to do that for that period of time is because FPGAs allow you to do circuitry with rapid iterations. So the entire point of the field programmable nature of the FPGA, the field programmable gate array, gives you that ability to iterate your designs and try things out instead of having to do all the design up front and kind of cross your fingers and get yourself painted into a corner.
And not just that, you can implement something and then decide after you've gotten it working that it's not the way you wanted to go. We switched from a prefetch engine to a proper L1 cache. We switched from the original Super H, what was it, LLP. They had their own coordination mechanism, and we went to a more conventional comp exchange after we had the previous one working, because we had the luxury of being able to go, okay, we tried it, and now we know, and we want to do something else.
So today you can get boards and platforms from various different places that will run J-Core. These are some of ours. on the left-hand side. The one up on the right corner is from a colleague of Rob's in Austin, Texas. The one in the center here is we call it the Turtle board or the JX platform, and that is a fairly large Xilinx FPGA. There's about 30% of it used for system-on-chip base that includes 2 CPU cores, memory controllers for low-power DDR. Also includes things like Ethernet. So basically, you get a Raspberry Pi equivalent board with half an FPGA, half a very large FPGA available for you to do whatever you might do in it. And I'll show you a board in a couple slides that fits on top of this as to why that's a cool thing. And the one up on the left,
Pi 2/3, but not 4. 4 uses a different case, but ours will fit in a Raspberry Pi 3 case.
So the one up on the left hand at the top is a Kintex 7, very large FPGA. That's what is it?
It's under the heat.
It's a 160. It's under the heatsink. The full up system on chip base is about 5% of that FPGA, and those boards are available to do all kinds of really cool signal processing kind of things.
We filled up the rest of the space with a lot of very large, very fast DSPs and a DMA engine that handled 64 channels.
Tools and components, of course, is important. We use GHDL internally for all of our development. It's kind of interesting. One thing about open source, I'm sure everyone here on this call knows, proprietary tool chains, proprietary compilers always have bugs that the vendor doesn't fix, maybe grandfathers across. GHDL is pretty close to language reference manual compliant, the standard for VHDL.
They actually take bug reports when they're not.
And they take bug reports when they're not. And Yosis, they have a testing suite to make sure that they are for Verilog as well. So these are the gold standard for not only open source, but including all commercial implementations. That's our opinion, and we're sticking to it. Those are the gold standard. J1 and J2 have test benches. You can download them and without any hardware simulate and extend on your desktop in simulation. And then, of course, all the rest of the tools that programmers are used to, a complete set of Anuncie libraries and compilers are available. All the scripts to build all of the tools. We're thinking, and we might need a Docker image to put all of these things together into something. Internally, we use virtual machine image, and it's a little bit unwieldy. The main issue, of course, is that there are many components, many toolchain components that you need to get together, and at the moment, it's a bit of a hurdle to get over compiling and installing all of the tools.
Rich Felker and I build everything from source because we're the crazy people who do that. We do not expect anyone else to do that. They need something that just works.
So our GitHub repositories are organized into a hierarchy. You can grab not only the manual for the board, but also the design files for one of our boards. The CPU core is there, the system on chip base that will assemble together for you a complete microcontroller, and some really interesting peripheral cores. Have a look at the JCore-JX Turtle platform board. All the files are there. And of course, if you're on a small device like an ICE40, then JCore J1 GHDL is a tiny little design that you can use for that.
JX is the official name for the Raspberry Pi form factor board. Turtle was the development name. We're supposed to stop using it, but you know, it's kind of burned into our brains.
It is what it is. So in the background here, this is a pipeline for our GPS receiver baseband that we made available a few weeks ago. This particular IP core uses a J2 SMP system with Linux, and the signal processing is split between hardware and software. It's a really good example of the kinds of things you can do with an FPGA plus an open CPU core plus something else, whatever that else happens to be. In this case,
abuse of task set.
Yeah,
we're trying to get hard real time out of Linux, and it doesn't want to give it to us, but we had a large rock.
Yeah, so I mean, you can use the FPGA to solve some of the hard real-time problems, but generally speaking, this is an application where you couldn't use a Raspberry Pi. Even if the CPU cores were faster, you would still need an FPGA to do this. You can take this this GPS receiver reference design, for instance, and add something like motor controllers and make your own autonomous vehicle. It's a really interesting kind of thing. And scaling, as we talked about, both upwards and downwards, and I won't belabor that. So getting started, when Hitachi did this, only a big company could. Small boards are available, installation of the tools. There's another talk today about that. Template RTL is there. It can be modified to do some cool things. And after that, it's as simple as developing software. You can modify the CPU core just as if it was a piece of your software. Turtle platform, as I mentioned, everything in a soft core, J2 SMP, 63 megahertz. It's a little bit slow, but again, that's because FPGAs are now just catching up with the process technology of the 1990s. There's a lot of overhead in the FPGA, so that's to be expected, but it's still a practical device. Standard Raspberry Pi type peripherals are available, and there's some work in progress to do, which we certainly hope people contribute to. This one's a mature design. We did it in 2017, and even the board layout is available for you to reuse and change.
That big expensive FPGA with the heatsink on it, we had it running, I think, a little over 100 megahertz on that. But the difference is a Spartan 6 is a $20 chip, and that FPGA was mid 3 digits, I think.
Yeah.
Yeah.
So here's an example at the other end that's not a dev board. This is, well, it's sort of a dev board. This is what I call Open42S. If there are engineers in the crowd, the HP42S is sort of the pinnacle of calculators. If you're from the HP side of the fence and not the TI side. This is an example of a 2-chip solution to recreating that calculator with the excellent FreeE42 re-implementation in software running on a J-core. It's 2 chips. There's a Lattice FPGA and an SPI flash. There's sort of hand waving because it's also power supply, but that's fine. It pulls 77 microamps in standby current. Every keystroke, there's 1 milliamp for about 100 milliseconds. You get 6 months of battery life. This is a practical example you could use to build a user interface for maybe a CNC controller or something like that. This one is actually really interesting. This is our GPS hat. Inside the can there, you see in the background, is just RF receiver to digital IF. It produces samples at 16.368 megasamples per second. There's no processor on this board. It's not a GPS module or a GPS system in package chip. It's just the RF. And that goes to the Turtle board's FPGA, where there's the peripheral core for the GPS correlators, and the J2 does all the solution. This shows you how to do that kind of thing, and you can add this to your own board and suddenly have time and location.
I'd like to say a couple of things about both of these boards. The calculator board from the previous page, when I was saying there's the 2-chip solution that you can scotch tape to a watch battery, That's basically the brain of the calculator. The rest of the calculator is providing I/O devices and a form factor where you won't accidentally drop it and not be able to find it again. For the GPS, you are receiving real-time signals where what you're trying to measure is speed of light propagation delays, where time differences are literally measured in nanosecond, not nanoseconds, some of them in fractions of a nanosecond. So the hardware has to receive this, process it, and deliver it to the Linux system as packets of historical data with timestamps that say, at this time we saw this, because just getting it from one side of the board to the other side of the board and loading it into the processor is already enough signal delay that it's gone past, something else has already happened. So everything you're doing is processing, okay, here's a historical snapshot of what I saw. What did that mean? And then you have tracking loops that need to be updated in microseconds, where you have to respond to say, okay, I understood the data that I saw, adjust the filters of what you're looking for so that the new packets that are coming in are processed in this way so that I'm filtering for this signal for the specific satellites I'm tracking. So there's very hard real time that the hardware is having to deal with. And then there's still very real time, but measured an order of magnitude more leniently, which is still, a human will never even notice that it happened because microseconds are still insane. You know,
So
there's multiple layers of real time going on here. It took us, 2.5 years to get this sucker to actually work. But we finally did, and we're very proud of it. And we've released large chunks of it on GitHub.
So that's the kind of thing that an FPGA makes possible, and it's really sort of an exciting time to be working on this kind of thing, where all of the open tool chains are coming available, so that everybody can get their hands dirty.
Not just an FPGA, we also needed Linux because we're doing a lot of signal processing on the resulting packets, and the availability of a full Linux system where we can go, okay, this part needs to go out and do some floating point stuff and the Leibniz determinants and all those kind of things. Chunks of processing, you know, we have a GUI that is it's a text mode GUI, but it's displaying, here's the tracking data we're seeing. We have, you know, Linux being normal, providing a certain amount of user interface and just general plumbing, you know, scripts and stuff. And then we have, here is a real-time chunk where we've task set something to a processor that is running at sched RR priority. And then here is the correlator within the FPGA, and then here is the carefully tuned signal path that Martin did so you don't get feedback with data being handed off from the GPS hat into the GPIO pins and stuff. We've got like 4 layers of time time constraints, even down to the GUI can't be that sluggish or you're not, you know, you're not happy as a user. That the FPGA provides the flexibility to scale all the way to we're doing funky signal processing things on the input to we're running Linux and we want to tune Linux slightly using normal system administration methods.
So I think sort of as a takeaway from that, all of this is available for other people to build on. Yeah, I think that's sort of a message that I want to make sure everybody understands. So if you want to do this kind of work, we're making that stuff available to the open source community so that you can then take the basic implementation and do something really cool with it. So there we are. Any questions or
yes.
Yes.
Yeah, there's quite a few questions, but we've got like basically like 5 or so minutes, so I'll pick some out,
Yeah.
and maybe you can answer. We can do this over email afterwards. That might be easier. So
Sure. We also have a mailing list.
Yes. Yeah. So Drew Festini asks, for Linux on no MMU, is there a way to support shared libraries and user space? I believe ARM has FDPIC
Yes.
ABI for that.
We had FDPIC first. Well, yeah, we've had FDPIC working for a few years. FDPIC is basically ELF with extra data, so that the 4 main segments have been broken up so that they can independently load into different chunks of memory. The text segment, the data segment, RO data, and BSS don't have to be contiguous. But other than that, it's normal ELF. It's normal ELF with a bit set in the header saying I'm slightly different, and then some extra annotation in the tables. And then the compiler builds things with, instead of 1 base pointer, it has 4 base pointers. But other than that, I mean, there's a little bit of difference, but it mostly acts like ELF. And in fact, on systems with MMU, the security people are interested in FDPIC because it's kind of ASLR on steroids. You can relocate everything independently, so there's even more relocation to screw up people's no-op slides.
So yes,
so, yes, you can.
Yeah.
We mostly don't bother because we're old embedded people, and it's like, here's a statically linked binary, and I don't have to care about dependencies. But you don't have to. Muscle libc supports it just fine.
The base system that you come with has libc as a shared library right now.
Muscle libc specifically is the one we're using, but the maintainer is on our team. So.
And I believe they're also the maintainer for Super H in Linux as well.
That's correct.
Yes. Well, we kind of asked him to do that with, we signed a check and asked him to do it because, he's on our team.
Great stuff. Okay, another question. On RISC-V Kendryte K210, we can really only run on 1 BusyBox instance before running out of 8 megabyte SRAM memory. I'm curious how JCore handles it.
It just doesn't need to be that large. I'm not sure exactly what the issue is, but 8 megabytes is probably enough. Our boards are quite a bit larger than that because we're DDR memory instead of probably SDRAM. But the other problem is RISC-V is sort of an inefficient instruction set architecture from an instruction set density point of view, which is kind of the reason we decided not to go with those traditional approaches, either Spark or MIPS. But I don't think that that's the reason why. I think there's just things that can be done to improve the situation.
Another possibility is if they're doing a no MMU system and they didn't have FDPIC available, they may have done PI, position independent code, which does allow the binary to be completely relocated, but it doesn't break up the segments into 4 independent chunks. And what that means is every instance of like bash, if you run 3 instances of bash, they won't share the read-only parts. They won't share the text section. They won't share the RO data because they have to be contiguous in memory. So they're writable sections. In order for those to be unique, they need their own copies of the read-only sections. FDPIC on NoMMU was invented to make much more efficient use of the memory, because if you're running 5 copies of bash, you only have 1 copy of the of the executable code, the text section, ELF text section loaded, and only 1 copy of the RO data loaded. So you only need to allocate your stack and your heap and your data section and your BSS. BSS is the memory that starts zeroed, so doesn't need to be stored in the file, but is otherwise global data.
Cool. Jeremy comments, RISC-V is not good at code density. Embed results confirm this. ARC is much better data comparison. Interestingly, ARC and Super H had the same compiler engineer, Jorn Reneke.
Yeah, it also has to do with the with the density of the instruction packing. So RISC-V is a 32-bit instruction for each and every instruction. It does have a 16-bit extension, but most people don't seem to implement it. The other thing that SH has, and some purists will call it sort of CISC-like instead of RISC attributes to it. When you start doing things like analysis of instruction frequency, you start to realize that some things might need to be fused together in order to get good performance, or you might need a more complex instruction than a RISC machine would do. So those are the two places where Super H does things differently than RISC-V. The instructions are very densely packed.
Super H valued instruction density during its design, and when we say it's a sweet spot in the history of chip design, one of the things we're talking about is CISC happened. It wasn't really designed. It just sort of occurred over many years. RISC was specifically designed as, here's a new idea where all of our instructions are fixed length, and that not only lets us simplify the circuitry, but it also allows a second execution engine to look over the shoulder of the first one and execute the next instruction if it doesn't interfere with this one, because we know where the next one starts without having had to decode it. It's like, that's really cool. But each one of those takes one clock cycle as part of the definition. And if you have something that inherently needs 2, 3, 4 clock cycles, you break it up into multiple instructions, which is part of what bloats your code and eats L1 cache lines unnecessarily. And what the Super H guys did is they went, well, we can take a RISC instruction set where every instruction is 16 bits. It's 2 bytes per instruction, fine. But we're going to microcode it anyway, so that if this instruction does need to take 4 clock cycles because it's going out to memory and there's a wait state coming back, and then it needs a post increment that also needs a clock cycle because it's operating on the result of a calculation or whatever. If you need 2 clock cycles, if you need 3 clock cycles, if you need 4 clock cycles, you can do it in one instruction. That's part of how they got the better density. It is a microcoded RISC, which seems a little bit like a contradiction in terms, but at the same time is the best of both worlds. It has the advantages of both approaches, and it's very simple, light microcoding that doesn't take a lot of circuitry to implement, because when the Super H guys were making their chip, the transistor budgets they had were tiny, and they had to be clever to fit lots and lots of stuff in there. Whereas
so
a few years later,
I'm kind of conscious of the time, Rob.
Oh,
so yeah, I just want to make sure we get as many questions as possible. Very specifically,
I can enthuse for a while.
Yeah, very specific. That's a good thing. Excitement's important. Very specifically, I just wanted to mention that the instruction encoding here is a front end, so it's a RISC pipeline that we have in Super H and in JCore. But there may be more than one issue into that pipeline for each very short 16-bit instruction. And we can move on from there.